All right, so let's start talking about electron configurations and also some orbital diagrams, which is kind of the same thing. So we'll put E- configurations here, and then we'll put our orbital diagrams here. So I have my periodic table above here. Again, all of this information is contained in the periodic table. You just got to know how to read it. And so what we're talking about here is electron configuration. So the first thing we have to know is how many electrons an element has. And remember that in a neutral element, the number of protons is equal to the number of electrons. And the number of protons is this number right here, right? So hydrogen has 1 proton, magnesium has 12 protons, calcium has 20 protons. And since they're neutral in this state, they have the same amount of protons as electrons. So hydrogen has 1 electron, magnesium has 12 electrons, calcium has 20 electrons. So let's start off nice and easy. Let's start talking about hydrogen with its 1 electron. So hydrogen, we have 1 electron. And if we take a look where hydrogen is, if you remember, this right here is the s block. So hydrogen's first electron is going to go into an s orbital. And you can see here that we are in the first column, so it's going to go into a 1s orbital. So what we write is 1s to represent the orbitals, and then we put a superscript 1 up here. So let's go over what this means. This first one is your n, so n is equal to 1 here. This letter is the letter designation of L. So L in this case is equal to 0. So it's S. And then this superscript number is the number of electrons in that L orbital. So we only have 1 here, so it's just 1. And so if we were speaking verbally, the way we would pronounce this is 1s1. We say the electron configuration for hydrogen is 1s1. It has 1 electron in its n equals 1 and L equals 0 orbital. Next up, we're going to go to orbital diagrams over here. And orbital diagrams are basically just a pictorial representation of the electron configuration. So we have our 1s orbital, and then you just draw a little box. Sometimes you'll just see a line as well. Either one is fine. And how many electrons do we have in this orbital? Remember, this orbital is this little house for this electron. Well, we only have 1. And so we put 1 electron there. Remember, you draw this half hook arrow, and then you can put it spin up or spin down. Technically, either is correct, but by convention, spin up comes first. So you just start spin up first. It's arbitrary, but that's just kind of the way it's been decided to do. So by convention, we put the up first. Cool. So there's our electron configuration and our orbital diagram for hydrogen. And you can think about what that means. So you can think about the picture of hydrogen right now, right? Remember, we have a nucleus that's positively charged, and then we have an s orbital. An s orbital is just a sphere. So basically what we're saying is we know there's a nucleus and there's a sphere around there, and the electron is probably somewhere within that sphere. Cool. Let's move on to helium. The first thing you got to remember about helium in terms of electron configuration, it's actually kind of right over here instead. It looks like it's over here in the p block, but it's actually still in the s block. Helium, 2 protons, so 2 electrons. So again, we're in n equals 1, and we're still in the s block. So the orbital that we're talking about here is the 1s, right? But now we have 2 electrons. How many electrons can fit in an orbital, in an s orbital? Well, 2. So we can put both of them here. So we say this is 1s2. The electron configuration for helium is 1s2. And then in terms of the orbital diagram, right, we can draw our box. We call this the 1s orbital. And then we have an electron pointing up, and then an electron pointing down. And so that's our pictorial representation of what's going on here. Let's keep going line by line or element by element. Now we're at lithium. So if you think about where lithium is, it's right over here. It's got 3 electrons, right? And we're going to read this like a book, left to right, line by line. So this would be 1s1, 1s2. So far we are at 1s2. We have not reached lithium though yet. Our next line, we will reach lithium. And so think about what's going on here. Your n is equal to 2, so you're talking about 2, and we're still in the s block. So what is this going to be? Think about it. It's going to be 2s1, because there's only 1 electron in that 2s orbital. So 2s1. And that's the electron configuration for lithium. Let's draw our pictorial representation, our orbital diagram for that. So we have a block representing the 1s orbital, and it's totally filled, so it's got 2 electrons in there. And then our 2s orbital is separate from our 1s orbital, so we draw in a different box or a different line, and now we only have 1 electron in there. And remember, by convention, we put spin up first. Let's move on. And then you can also think about this stuff, this n stuff, in terms of the Bohr diagram of the model. It's not totally accurate, but it actually represents a good bit of the data. And so in this kind of n equals 1 shell, we have 2 electrons. And then in this bigger one, right, n equals 2, we have 1 electron. So that would be the Bohr model for lithium. Our next element, if we take a look at our periodic table, is beryllium. Very cool element. And so again, we're going to read like a book from left to right, line by line. So this is 1s1, 1s2, 2s1, and then when we get to beryllium, we are at 2s2. So our electron configuration would be 1s2, 2s2, right? Beryllium has 4 electrons. And so we can draw our little orbital diagram, right? The 1s is filled. And now the 2s is also filled. If we take a look at our periodic table, next up is boron. And again, we're going to read it like a book, left to right, line by line. So here's 1s2, or 1s1, 1s2, 2s1, 2s2. Now what happens when we get to boron? Our n is still 2, but now we're in the p block. P block. So this would then be 2p. And how many electrons are here? Just 1. So 2p1. So the electron configuration for beryllium is 1s2, 2s2, 2p1. So let's see how we're going to draw the orbital diagram for that. So we have our 1s, 2 electrons in there. We have our 2s, 2 electrons in there. And then we have our 2p. This is where things get a little bit tricky. Think about how many p orbitals there are. Well, if it's a p orbital, then your L is equal to 1, which means your M sub L can equal to -1, 0, or 1. So there's 3 p orbitals. So we actually draw this kind of rectangular box or 3 separate lines, and then divvy it up into 3 boxes representing each one of the orbitals. And then by convention, you just fill the first one up first with 1 up arrow. And so there's your orbital diagram electron configuration for boron. And you can see the way this table is organized. We have 3 p orbitals. Each p orbital can fit 2 electrons, so 6 total in a p orbital. And if you look here, 1, 2, 3, 4, 5, 6. So exactly how many you would expect. All right, next up is carbon. Let's erase all this other stuff, right? So carbon's right there. Again, we're going to read it like a book, line by line, or left to right, line by line. So this is 1s1, 1s2, 2s1, 2s2, 2p1, 2p2. And we're at carbon. So carbon, 1s2, 2s2, 2p2. So let's think about how we're going to fill that. So we have 1s, it's filled. We have 2s, it's filled. We have our 2p orbitals, and there's 3 of them. And so we'll put the first electron here. And now here's where things get a little bit more tricky. You first fill up every orbital in the same kind of L and N, so the 2p, with 1 electron each before doubling up. So we put another up arrow here. So there's 2 things you have to remember here. Number 1 is put electrons by themselves, if possible, right, before doubling up. This is called Hunds Rule. Again, you don't have to know the name, you just have to know what it means. And then the second thing that we have to remember here is that your arrows must face the same way. So the first one I drew up, so the second one I must draw up as well. So arrows must face same way. Don't worry about the why. It's kind of a quantum mechanical reason for all this stuff, so it does get kind of complex. Again, we're just really kind of scratching the surface here. If you took chemistry in high school or at some other point, sorry about that. If you took chemistry in high school or maybe learned chemistry elsewhere, you may have seen some kind of diagram that looks like this. This tells you how to fill orbitals as well, but in my opinion, it's just way more confusing than using the periodic table. And I think it's actually kind of going away. I think less and less people are teaching it. So in my opinion, it's the same thing as using the periodic table. It's just more confusing. So what's the point? Cool. So good to go there.